Hello students, in this video you will be learning about drift velocity. Now consider a small segment of a metallic conductor. In a metal, you know that there are large number of electrons and all these electrons are free to move. And also they suffer from collisions. So this is the case when no electric field is applied to the conductor. So when no electric field is applied to the conductor, the electrons in the conductor are in random motion. Now, what is the average speed of these electrons? You have been doing several problems in your mechanics using Newton's laws, equations of motion to find the speed, velocity of moving objects. But this case is not as simple as that because now we are dealing with electrons. These particles do not have well-defined position, so they are called as quantum particles. But great scientists, they have computed the effective speed of electrons in a metallic conductor, and they have found that the speed, that is the effective speed, is of the order of 10 to the power 6 meter per second. So the electrons in the conductor are moving with such large speed. So how about the average velocity? The average velocity of electrons moving in a metallic conductor when no electric field is applied is 0. Why? Yes, because the electrons, they are all moving in random motion in different directions. So when you take the average, it goes to 0. Now let's consider the case when electric field is applied. When electric field is applied to a metallic conductor, the situation changes. Say, this is the direction of the electric field applied. Now, due to this electric field, the electrons, they are charged particles, so they experience force. That force is equal to minus E into E. The direction of this force is opposite to that of the electric field because the electrons are negatively charged particles. Now, because of this force, the electrons experience a push. So, they all move along the direction of the force with a velocity called as the drift velocity. Okay, so now when the electric field is applied, electrons move with drift velocity, and it is also possible to compute the magnitude of this velocity, and it is found that the drift velocity is of the order of 10 to the power minus 4 meter per second. So when an electric field is applied to a metallic conductor, due to the effect of the electric field, the electrons, although they are in random motion, they drift with such a small speed of the order of 10 to the power minus 4 meter per second. As a result, now the charges flow and hence a current flows through the conductor. So this is a story. Now, as an analogy, I can say the case of gas molecules. You know that gas molecules, they are all free to move. They collide with each other. But think of the case of breeze. Okay, so although the gas molecules are in random motion, they suffer from collisions. When there is a breeze, they all drift as a group. So that is a similar situation in a metallic conductor when an electric field is applied. That is, the random collisions of the electrons superimposed on that is the drift movement along the direction of force applied. Okay, now let's try to derive an expression for the drift velocity. Okay. Yes, an expression for drift velocity can be obtained. Expression for drift velocity. Yes. Okay. So now we have already discussed in detail how the electrons move in a conductor when an electric field is applied. Now, when the electric field is applied, we know that the force is given by F is equal to minus E into E. Now, by Newton's law, we know that due to this force, the electrons experience an acceleration. Okay, so the acceleration is given by A equals F by M. So it is minus E by M. Now let's consider a particular electron, say ith electron. Okay. Now the electron, suppose that this electron is situated at a particular location, say 1 at time t1, and it is moving inside a conductor, so it's suffering from collisions. Okay, so this is the kind of random movement of the electron, and finally it has reached to location 2. Okay, so this is the movement of the electron when no electric field is applied. Now let's consider the situation when an electric field is applied. What will happen? There will be a drift along the direction opposite to that of the electric field. So suppose if this is the electric field that is applied, the electron would now drift in a particular direction. So maybe the collision will happen here, and here it goes, and then the movement will be like this. Okay, so here the movement of the electron goes, and then here it is, and finally it will reach another location, say location 3. Now let's consider the electron at location 3 at time t2. Okay, so we already know that the electron had suffered a collision at location 1 sometime earlier than t2, say t1. Okay, so now let Vi be the velocity, be the initial velocity after collision. Okay, Vi is the initial velocity of the electron after collision at location 1. Okay, so then what is the time elapsed? Time elapsed is the time taken by the electron to travel from location 1 to location 3 as the effect of electric field. Okay, so the time elapsed may be taken as t, so it is equal to t2 minus t1. So now we are ready to find the final velocity of the electron. Okay, final velocity of the electron at the time t2. We know the initial velocity, we know the time taken, so it's very easy to find the final velocity using the equation of motion. That is, the final velocity is equal to the initial velocity plus acceleration into time. So now this is a case of one single electron, that is the ith electron, and we know that in a conductor there are n number of electrons. Okay, so now we can find similar equations for n number of electrons, and if we try to take the average, okay, now we are trying to take the average of each and every term of this equation, okay, for n number of electrons, then what will be the situation? Okay, on the left hand side, the average final velocity of all the electrons, n number of electrons in the conductor, would give you the drift velocity. That is the drift velocity with which the electrons would be moving. And how about this term? The average initial velocity. Okay, so here we know that this is the velocity after collision. So the electrons are all moving in different directions after collision. So what will happen if I take the average? This term would average to 0. So what are we left with? We are just left with this term, and we know that acceleration is given by this equation. So substituting for acceleration, we arrive at the relation for drift velocity as Vd equals minus Ee by m, and the average time taken is now changed to tau. Okay, so this is the equation where tau is the relaxation time. Relaxation time, or this is also called as the average time between collisions. So this is the expression for drift velocity of electrons moving in a conductor, and it should be noted that the drift velocity is independent of time. Okay, so the electrons in a metallic conductor are all drifting with a uniform velocity given by this expression. Thank you.